Hello students, welcome to the series of lectures on linear integrated circuits and applications. So in this video I am going to explain this classroom discussion topic on first order active low pass filter, which is the first topic in unit number 3. Okay, and the comparison of all the frequency responses of the filters that has been already made a video, that is a self-learning topic, so please watch that video also. Alright, so let's get started with this topic, first order active low pass filter. Alright, so these are the two lecture learning outcomes we'll be having. So on completion of this lecture, you'll be able to understand the op-amp based active filters, and you'll be able to analyze the operation of the first order active low pass filter. So these are the two important lecture learning outcomes you are going to be getting from this lecture. Alright, so this is a pin diagram. In every video I am putting the same thing. Please go through this pin configuration of IC741. Alright, see the first order active low pass filter. So see here, what is a low pass filter that we already know. A low pass filter is a filter which allows low frequency components and which rejects all the high frequency components. Okay, so the same thing I have mentioned in this slide, filter that passes the frequencies from 0 Hz to cutoff frequency FC. That is our designer specific. Okay, because we are designing the filter, right? So now we need to specify at what frequencies we need to allow the signal. Okay, so this is a cutoff frequency that we need to decide. Okay, so all the frequencies from 0 Hz. Okay, this is a DC signal, let it be. Okay, so DC to cutoff frequency FC, and significantly which attenuates all other frequencies. That means above cutoff frequencies, all the frequencies will be attenuates. That's the meaning of this. Okay, and when you look here, so this is a basic low pass circuit. This is a circuit diagram. Okay, listen. So here we'll be having what? So normally this is the help of what? A resistance and then capacitor. We have not included any operational amplifier. Please understand, because this kind of circuit that you already studied. Okay, only resistor we have taken, capacitor we have taken. Okay, and we are taking output across the resistor. So that's the meaning of the low pass filter. We are applying input as a sinusoidal to the input to the resistor. Okay, and you are going to be taking the output across capacitor. So this is the simple passive components we have used, only resistor and capacitor. This is the way how we need to construct the circuit low pass filter. Okay, now this is the ideal response. Okay, for low frequencies the gain will be maximum, and if you increase the frequencies from here, the gain will be constant for some duration, and then it will fall down from maximum to the minimum. So this frequency I am calling as cutoff frequency. Okay, this frequency I am calling as cutoff frequency. So obviously these are the frequencies of the signal which allows. So that is the reason I am calling this the pass band, and this is a region where all the signals of frequencies will be attenuated. So this is the stop band. So this is an ideal response, but practically it may not be the same case. Okay, so practically, so here the left hand side you can see this. This is an actual response, or the practical cases. This kind of waveform we are going to be seeing. Okay, so frequency on x-axis and the gain in decibels on y-axis we have taken. Same here, from low frequencies the gain should be maximum, and if you increase the frequencies from here, the gain will be constant for the duration, and then it will fall down. So this is the roll off rate. Okay, so in the previous unit also we have clearly mentioned what is the roll off rate. Okay, so for the first order we'll be having the roll off rate should be minus 20 dB per decade. So that's the meaning of this. Okay, so minus 20 dB per decade. For every 10 increments of frequency, the gain will be fall down by 20 decibels. So this is the general how we are going to be describing the filter. When you want to construct that as a low pass filter, this is the way how we are going to be looking. Okay, this is the circuit which is consisting of only passive components. Okay, we have not included the active component as operational amplifier. Okay, now let us focus our discussion on first order low pass Butterworth filters. Okay, so Butterworth is a scientist. He has designed the circuit of the low pass filter with the help of the operational amplifier, and we have so many other kind of filters which are also available, including Butterworth. Butterworth is one category, and then Chebyshev filter is there, and Bessel filters are also there. Okay, among these three, so this Butterworth filter is the best suitable filter in the practical applications, because if you choose the Butterworth filter which is approximately identical to the ideal response, okay, that's the reason we are always concentrating on designing of Butterworth filter only. Okay, so what is Butterworth filter? What's the point I have mentioned here is Butterworth filter is a type of filter so whose frequency response is flat over the pass band region. That is what I have mentioned. Okay, which is approximately similar to the response of ideal. Okay, right. Now coming to the second point, the low pass filter which provides a constant output from DC up to a cutoff frequency FH. Okay, for low pass filter we'll be having the higher cutoff frequencies and which rejects all signals above that frequency. Okay, so just before we already seen in the previous slide. So the first order low pass Butterworth filter is realized by RC circuit used along with an op amp. So this is what our interest. Okay, so this is a active device. Okay, so in the previous example what we have seen is that is a passive components we have used for the construction of low pass filter. Now along with the passive components we are going to be using the active component as operational amplifiers. Okay, and which is used in the non-inverting configuration. Okay, that you are going to be using in the non-inverting configuration. So let's focus on that. All right, so this is the circuit diagram. Okay, so this is the circuit diagram of a first order Butterworth low pass filter. Okay, circuit diagram for the Butterworth low pass filter. So here you can easily identify the same thing whatever I have mentioned the point in the previous slide. So this is the passive components. R and C pair will be connected to where? Non-inverting input of operational amplifiers. Okay, so this is the way how we are going to be looking at the circuit diagram. Okay, now we are taking the output across pin number 6. Okay, this is pin number 7, this is 4, and this is 2, and this is 3. Don't forget the pin configurations of IC741, which is very important. That is the reason I am always almost in all the videos, in all the PPTs I have mentioned the pin configuration of IC741. Okay, all right. Now let us discuss about the analysis of the filter circuit. Okay, so see the circuit diagram here. This is the circuit diagram for low pass first order Butterworth filter. What is the meaning of first order? First order means only single RC pair we have chosen. Okay, that's the way how we are looking for the circuit. Okay, so in the circuit we'll be having R and C. That's the first order. For example, if I ask you to design the second order, we'll be having the two RC pairs at the input side. That becomes second order. And if I ask you to design the fourth order, 4 RC pairs, like that. Okay, you can understand from that. Now coming to the analysis part. So here in the left hand side of the PPT, so the impedance of the capacitor C is minus J times of XC, where XC is the capacitive reactance which is given by XC equal to 1 upon 2 pi FC. Okay, which is the frequency component. And by the potential divider rule, the voltage at the non-inverting input terminal. Now we need to calculate the output voltage of the filter, right? Before that, first we need to put our efforts for calculating the what is point A. If the operational amplifier is ideal, then whatever the voltage that we are calculating across capacitor, the same will be reflected across point B. Okay, so let us do the voltage divider principle. We'll be having VA equal to something like this. Okay, and if you rearrange the terms, and we'll be having VA equal to something like this. Okay, point number 2. Okay, now in continuation to the previous, see, as the op amp in the non-inverting configuration, this is the formula is pretty straightforward for us. V0 equal to 1 plus RF by R1 times of VA, not V in now, because This point we have already calculated in the previous slide, this voltage. So that voltage we need to substitute in the formula. You'll be getting V0 by Vin equal to AF by 1 plus J into F upon FH. So this is the gain equation. This is the gain of filter. Alright. So what is AF now? AF nothing but gain of the filter in pass band. Okay, this is the closed loop gain, particularly speaking, which is the closed loop gain of the filter. Okay, and what is FH? FH is nothing but 1 upon 2 pi RC. That is a higher cutoff frequency of the low pass filter. And where normal F, which represents the operating frequency or the input signal frequency that you are applying here at the input side. Okay, so this is the gain equation. Now let us look into the frequency response plot. Okay, the frequency response plot that can be possible from this equation only. If you take the magnitude of this and if you apply the phase angle, then you will be having the magnitude response plot and also phase angle response plot. Okay, now let us restrict our discussion to only magnitude response plot only. Okay, that we can see. Alright, so this is the practical frequency response of the first order Butterworth low pass filter. Okay, so the frequency FH, which is nothing but the higher cutoff frequency, and we can also call this a break frequency or 3 dB down, because this is the maximum. Okay, this is a voltage gain, the linear value. If you want to convert this into decibels, okay, if you want to convert this into decibels, you will be having 20 log this A into the base 10. So that is a way how we are going to be converting into decibels. 20 log A into the base 10 dBs. Okay, so after converting the linear value into the dBs, and we can easily find out what is happening at this region. This is 0.707 AF. In terms of dB, it will be minus 3 dB down. So this is minus 3 dB down. That is the reason we are calling FH is a higher cutoff frequency or 3 dB down frequency. Okay, so from this, if you project onto the plot, and from here this point, if you project onto the x-axis, that frequency is the higher cutoff frequency. So this is the frequency response plot of the first order Butterworth active low pass filter. This is the stop band and this is the pass band region. Okay, and the slope should be decreased with a rate of 20 dB per decade, that we already explained in the previous slide also. This we can also call as a roll off rate. Okay, so that's pretty much about this topic. Thank you, students. Thank you for watching this video.